In this video, we're going to spend some more time looking at the derivatives of exponential and log functions. We've already met the chain rule, the product rule and the quotient rule and worked through a range of algebraic, trig and basic exponential and log derivatives. We're now going to look at putting all of that knowledge together and work through some further examples. In the video on the exponential function e to the x, we saw that if y was equal to e to the x, the derivative dy by dx of a gradient function was also e to the x. The number e is just 2.718, correct to 4 significant figures, and it gave us now an exponential curve. So we ended up with something now that was defined for all real values. So e to the x is defined for all real values of x, and it had a range now where y was going to be strictly greater than 0. So if y was equal to e to the x, then dy by dx was also equal to e to the x. This is a standard result that we can quote, and we certainly don't need to prove it from first principles. In general, if we have an exponential function, y is equal to a to the x, where a is a positive constant, the derivative, as we will see in a later unit, is a to the x multiplied by the natural log of a. So let's see why we just end up with dy by dx. This is certainly not a proof, but it might help you understand why we have now simply e to the x here. If we consider now at this stage right here, we would have dy by dx would be equal to e to the x multiplied by the natural log of e. Now e to the x and the natural log of x are inverse functions. If we have now the natural log of e, that gives us 1. Hence why dy by dx is simply e to the x. We're going to quote that standard result throughout the video. We also looked at the standard result for the derivative of the natural log of x. If y was equal to the natural log of x, then the derivative dy by dx, the gradient function, was 1 over x. And we just took this as a given. What we're now going to do is look at now deriving this. We're not going to do a proof. The proof, again, is quite involved and certainly beyond the scope of the course. But what we're going to do is just show basically why the derivative of the natural log of x is 1 over x. There are lots of different approaches that you could take to show this, but using the knowledge that we have, we can apply one of the results of the chain rule. So if we take the chain rule, you see now in the chain rule that if we have dy by dx, and we can write it just here, dy by dx will be equal to 1 over dx dy. So what I'm going to do is use this result to derive now the derivative of the natural log of x and show that it's 1 over x. So if we have now, we'll say let y be equal to the natural log of x. If y is equal to the natural log of x, we can say the equivalent exponential statement is e to the y is equal to now x. If you want to show that e to the y is equal to e to the natural log of x, you can do, but this is an equivalent statement. At this stage, I'm going to differentiate both sides of the equation with respect to y. When we differentiate e to the x with respect to x, we get e to the x. Therefore, if I differentiate e to the y with respect to e to the y, with respect to y, we get e to the y. If I differentiate x with respect to y, we get dx dy. So all I'm going to do now is write that 1 over e to the y is equal to dy by dx. This is just now an application of the chain rule. If dy by dx is 1 over dx dy, we can simply write that just here. This is dx dy. At this stage, we can say that e to the y is equal to x, so we can write 1 over x is equal to dy by dx. So that's simply now deriving it. It's not a proof, it's certainly not a proof, and we wouldn't be expected to quote the proof or show the proof, but it is now deriving that result. What we'll do as we go through the video is look when we have functions of functions and look at how to apply this in any given situation. If we wanted to show this graphically now, we've got let's go ahead and draw the gradient function. Let's do that. So dy by dx, we've got the natural log of x. The natural log of x looks something like so. So we've seen the natural log of x in the video on the exponential and log functions. We have now this point 0, 1. It's simply a reflection of y equals e to x in the line now y equals x. We have now the derivative, the gradient function, and we'll put that on. Let's go ahead and do that. The gradient function is y is equal to 1 over x, and it will look something like that. So we'll come round and we'll have that. So y is equal now to 1 over x. And this gives us our gradient function. So as we can see, as x gets large, now the gradient of the natural log is going to get smaller and smaller. And this tends to positive infinity incredibly slowly. So you can hopefully see now the shape of the graph there. So let's just label that up. Let's go ahead and write now y is equal to the natural log of x. We saw that with the natural log of x, we had a domain where x was going to be greater than 0 and y was all real numbers. And that was because when we had the exponential e to the x, the domain and the range got flipped over. So if this was now e to the x, which looks something like that, we had 0, 1, and we had a reflection. So this is just going back to some basic work on looking at these two inverse functions. So there we go, that's y is equal to e to the x and then the natural log of x. So y equals e to the x, and also now dy by dx equals e to the x. Let's start off with some work now looking at functions of functions and their derivatives. So we'll start with a nice straightforward. Let's go ahead and look at y is equal to e to the 2x. So we have a function of a function. We've got now the exponential function e to the x, and we've also got this linear function 2x. We can use the chain rule. If we wanted to find now dy by dx, we could go ahead and use the chain rule. We can say that the chain rule, as we've seen in the previous videos, dy by dx is dy by du multiplied by du dx. So in this particular case, we could let the inside function now, which is 2x, be equal to u. So let u be equal to 2x. So we have y is equal to e to the u. I'm looking for an expression now, dy du, and one for du dx. So at this stage, if we differentiate now y with respect to u, we can say dy by du will be equal to e to the u. This is just simply differentiating e to the u. The derivative of e to the u with respect to u is e to the u. If we look now at du dx, that is the derivative of u with respect to x, which is 2. So in terms of y, we can say now, or in terms of dy by dx, we can say that this is 2e to the u. We can write here, but u is equal to 2x. So we can say in terms of x, the derivative dy by dx is 2e to the 2x. That is a very long-winded way around the chain rule, and you wouldn't be expected now to use that each time. In general, if we have now y is equal to e to the f of x, so here I'm looking at a function of x, we can say from this stage right here that dy by dx will be equal to f dashed of x multiplied by e to the f of x. So what is this saying? This is simply telling me now that if I want to differentiate an exponential function, where I've got a function of a function, all I do is multiply the original function by the derivative of now this inside function. The reason being is when we differentiate the outside function, it remains exactly the same. So if we look, for example, now at y, let's go for y is equal to something really quite more involved. Let's say e to the 3x to the 4th minus 7x cubed, let's write that there, plus, let's go for 5x squared plus 3x minus 10. All we would do is simply find the derivative here, so we could say that dy by dx, we are differentiating the outside function. The outside function is e to the x, the derivative of e to the x is e to the x. So we would simply now write e to the inside function, we'd leave that inside function alone, 3x to the power 4 minus 7x to the power of 3 plus 5x squared plus 3x minus 10, and then multiply this by the derivative of the inside function, which will be 12x cubed minus 21x squared, and then we'll have the plus 10x plus 3. And obviously differentiating the constant minus 10 will give us now 0. So this is what we have. We have now 12x cubed minus 21x squared plus 10x plus 3 multiplied by e now to the 3x to the 4th minus 7x cubed plus 5x squared plus 3x minus 10. That is it. You're simply now taking the derivative of the inside function and multiplying it through now the original function. So let's do one more. If y is equal to 4e to the 5x squared plus 2, then we can say that dy by dx, I'm simply now going to multiply the derivative of the inside function. The derivative is going to be 10x. We'll have 10x multiplied now by 4e to the 5x squared plus 2. So the derivative of the inside function multiply, which is going to give me now 40x e to the 5x squared plus 2. So that's looking at a function of a function using the chain rule informally. I've used it formally here. You can see that's going to take a lot of time, but in general, if we have now y is equal to the fe to the f of x, the derivative dy by dx is f dash of x multiplied by e to the f of x. You can, of course, extend that to functions of functions, whether if the inside function isn't an algebraic expression or algebraic function. Let's say we had now y is equal to, let's say, 3e to the sine of 2x. So we've got now a function of a function of a function, essentially, but we'll just treat this as the inside function. Now, if you're not confident at this stage, you could say now, let u be equal to that inside function, sine 2x. So we have y is equal to now 3e to the u. So we could use the chain rule, dy by dx is equal to dy by du multiplied now by du dx. So if I differentiate now y with respect to u, I can say that dy by du will be equal to 3e to the u. If I look at du dx, I'm going to differentiate now u with respect to x. And again, this is a function of a function, but we've seen in the previous video, if we have y is equal to the sine of kx, the derivative is k cos of kx. So the derivative of sine 2x is 2 cos 2x. Essentially, we differentiate the outside function, we rewrite the inside function and multiply through by the derivative of the inside function. So we can now say that dy by dx is the multiple of these two. So we're going to get 6e to the u cos 2x. But we know that u is equal to sine 2x, so we can write now that dy by dx will be equal to 6e to the sine of 2x multiplied by cos of 2x. And that's the derivative. If you like, all we've done now is simply multiply the function by the derivative. You can see all I've done is multiply that by 2 cos of 2x. So that's an example now where we have an exponential and a trig function. We might also have products. We might have a product or we might have a quotient. So let's say we've got y is equal to 5x squared multiplied now by e, and we'll go to the power of 3x minus 1. So what we'll do is simply use the product rule. We've got this algebraic function and we've got now the exponential function. And this is of the form y is equal to u multiplied by v, where u and v are both functions of x. We've seen if this is the case, we can use the product rule. And the product rule says that dy by dx, the first derivative, will be v du dx multiplied by u dv dx. Or, if you like, the first function multiplied by the derivative of the second, plus the second function multiplied by the derivative of the first. And that's what we spent a video looking at. So what we've got then in this particular case, let's go ahead and do that. We will have now u. Now what I'm going to write just here is that dy by dx, I'm going to take the constant out. I'm going to have 5 lots now of a quantity. So what I'm going to have is u is equal to x squared. You can, of course, say 5x squared. It just means taking the constant out. The number crunching becomes slightly less. Derivative du dx, so we're differentiating now x squared, 2x. If we take v, we've got v to be e to the power of 3x minus 1. The derivative dv by dx by the chain rule, function of a function, 3e to the 3x minus 1. I've just taken the derivative of now the inside function and multiplied it. We need to multiply these two. That's v du dx. So we get 2x e to the power of 3x minus 1. And we add to it the multiple of these two. So plus 3x squared e to the 3x minus 1. And that will give us now the derivative. And you might be asked to factor this or show that it can be written in some form. So we'll go ahead and do that. And we might also be asked to find stationary points, or we might be asked to find the gradient at a given point, or we might be even asked to find a tangent or normal. In one of the exam style question videos, we will look at finding tangents and normals. For now, I'll just tidy this up. So we got dy by dx. So we can take a common factor now of x e to the 3x minus 1. So taking that common factor out of x e to the 3x minus 1, that's going to leave me now 2, and then we're going to have plus 3x. So I've just factored that. So if we were asked where this was stationary, so we can write just here, so for SP, if we just had an unrestricted domain in this particular case, we could say now for stationary points dy by dx would be equal to 0. Therefore, what we would have now is that x would be equal to 0. We would have the content of this bracket equal to 0, so we could say x was equal to minus 2/3, and then we have e to the 3x minus 1 equal to 0. Now e to the 3x minus 1 can never be equal to 0. So the x-coordinates of the stationary points now are going to be 0 and minus 2/3, and then of course we could plug those in to find the y-coordinates. So that gives us some idea on the work that we could do if we were given now a product. So that's just applying the product rule with an exponential and an algebraic function. The vast majority of these derivatives involving the exponential function are fairly straightforward. It's rare that you would be caught out in anything. One thing that might be less enjoyed by students is something along the lines of y is equal to 1 over 4 e to the power of 3. We could simply write this now as y is equal to 1, let's put e to the 3x, 1/4 now e to the minus 3x. So our derivative dy by dx would simply now be multiplying through by the derivative of the inside function. The derivative of the inside function now is going to be minus 3, so we have 1/4 e to the minus 3x. And of course you could write that as minus 3/4 e to the minus 3x. That's just something to be aware of. Let's now move on to the log function, the natural log of x, or ln of x. So let's say we have now y is equal to the natural log of 2x. We want to find a derivative. We can do this either formally using the chain rule, or we can do it informally, and later on it will be expected that you just essentially follow an algorithm. For now here we have a function of a function. So function of a function says the chain rule. dy by dx is dy by du multiplied now by du dx. So we can say at this stage, let u be equal to the inside function. So we've got the natural log of x, which is the outside function, 2x, which is the inside function. We can say that now y is equal to the natural log of u. dy by du, the gradient function for now, y with respect to u will be the derivative of the natural log of u. We've seen that will be 1 over u, and that's our standard result. Therefore, now we look at the natural log, we look at the derivative of u with respect to x, so du by dx will simply be 2. We can write this now as dy by dx is the multiple of those two. It's dy by du multiplied by du dx. So we have 2 over u, but of course u is now 2x, and we can write that dy by dx will be equal now to 2 over 2x, which gives us now 1 over x. And I'll just write that there. So we can see that if we have now this linear function here, the natural log of kx, the derivative is still 1 over x. In general, we can say if y, and we'll write it here, if y is equal to the natural log of a function of x, we've got dy by dx will now be 1 over that function of x multiplied now by the derivative. So a nice way to remember this is 1 over the inside function multiplied through by the derivative of the inside function. Of course, we could go ahead and look at quite a nasty example of that. Let's say we had y is equal to 3 lots of the natural log and then some polynomial. Let's say we've got now 4x squared plus 3x minus 7. So if we look at this, we can say the derivative dy by dx, 3 is just a constant. We're going to have now 3 lots of 1 over the inside function. This is the inside function. 4x squared plus 3x minus 7 multiplied through by the derivative of the inside function, which is going to give me 8x plus 3. So that, when we tidy it up, is going to now be our derivative. And we could look to factor these things and tidy up, but ultimately that's what it is. It's 1 over the inside function multiplied through by the derivative of the inside function. You can, of course, at this stage say that u is equal to this inside function. So if you wanted a more formal approach at this stage, you could say now let u be equal to the inside function. So u would be equal to 4x squared plus 3x minus 7. So we'd have y is equal to 3 lots of the natural log of u. The derivative dy by du would be 3 lots of 1 over u. So we could write dy by du would be equal to 3 lots of 1 over u, or 3 over u. We could say that du dx would be equal to the derivative of u with respect to x, which is 8x plus 3. We would multiply the two, so we would say that dy by dx was equal to 3 lots of 8x plus 3 over now u, but of course we know that u was the original function, the inside function, and we could go ahead and write that. So dy by dx in terms of x would be 3 lots of x, 8x plus 3 over now we'd have 4x squared plus 3x minus 7. Now, just looking at that here, I've chosen that particular function, that inside function. If we spent a little time looking at that, that's going to factor. And this brings us on to quite a nice little quirk, or at least one of the things that we could do in terms of the derivative of particular log functions. So let's look at another way that we could have done this. Sometimes it's more convenient to take this approach, sometimes it does simply involve more work. But if I now took this original, so we have the equation now, y is equal to 3 lots of the natural log of, and then it was 4x squared plus 3x minus 7. If I just check that, I think that's what we had. Yeah, there we go. So that's what we had. We know log laws, and often using log laws can make now the derivative easier. We know that the natural log of a plus the natural log of b gives us the product. So the sum is a product, the natural log of ab. The natural log of a minus the natural log of b gives us the natural log of a over b. If we have the natural log of a to the power of b, we can see that, say that's b the natural log of a. At this stage, I could factor this. I'm not suggesting in this particular case it would be any easier, but later on we'll see that some particular derivatives could be easier. So what we've got then is 3 lots of the natural log, and then we've got 4x plus 7, and then we're going to have now x minus 1. So let's just check. 4x squared minus 4x plus 7x minus 7. So we could write this now as y is equal to 3 lots, and then what we'd have now is the natural log of 4x plus 7 plus now the natural log of, and we're going to have x minus 1. So in this case, it's not going to be any more beneficial to do this way, but you can see that this particular property, and certainly the power law or power rule, will allow us some straightforward derivatives. So let's just look at this using exactly what we would have had. So dy by dx would be now 3 lots, and then we would have 1 over 4x plus 7 multiplied by the derivative of 4x plus 7, which is 4, plus 1 over x minus 1 multiplied by the derivative of x minus 1, which would end up giving us that. So if we look at this, dy by dx is going to be now 3 lots, and then we're going to have, with our single combined fraction, the denominator is going to be 4x plus 7 multiplied by x minus 1, and then we're going to have now 4 lots of x minus 1 plus 1, and that will give us now 4x. And what are we going to have on there? Let's write this out. So dy by dx, just writing this out now, is going to give us 3 lots, and we're going to have 4x minus 3. So let's write this in. 4x minus 3 over now 4x plus 7, and then we're going to have the x minus 1. So all I've done is gone ahead and differentiated that, and done it now step by step. Let's just check I've had it. In fact, I need to add my fractions, don't I? Let's see if I can actually add the fractions. What do we need? We need 4x plus 7, don't we? There we go. That looks better. And then what are we going to have here? Let's pretend I can actually add fractions rather than just leaving one of them. What are we going to be left with? We're going to have 8x. Let's put this in, 8x and then 8x plus 3. I thought to myself that wasn't looking too close to what we had before. So all I've done is combine the fractions. Let's just, hopefully that makes sense. So you can see, let's look back at the last derivative. There we go, exactly the same. 3 lots of 8x plus 3 over now 4x plus 7. It's just expanded. So if you can add fractions, if you can add algebraic fractions, you can see now that that is quite a beneficial route potentially to take if you need to split things up. So let's look at another couple of examples using that. So say we had now, let's say we had y is equal to the natural log, and we had now the cube root, the natural log of the cube root of 2x minus 7. We could write this now as y is equal to the natural log of 2x minus 7 to the power of 1/3. So using log laws, we can bring the power down, and we can say that y would be 1/3 the natural log of 2x minus 7. So we could say that dy by dx would be equal to 1/3. And then all we would do is write 1 over the inside function, which is 2x minus 7, multiplied through by the derivative of the inside function, which is 2. So we can say that dy by dx would be now 2 over 3 lots of 2x minus 7. So no algebraic fractions at that time, and hopefully you can see that it's probably simpler doing it with that particular approach. Again, some aren't, but some might be. Another example of where you may believe it could be is if we had now y is equal to, let's say, the natural log, and we'll have, let's say, 3x minus 2, and that was squared over now, let's say, 5x plus 4. So at the moment, this looks a bit of a mess. We've got a quotient, so we could write y is equal to the natural log of 3x minus 2 to the power of 2 minus the natural log of the denominator, which is 5x plus 4. So y is equal to, bringing the power down, 2 lots of the natural log of 3x minus 2 minus the natural log of 5x plus 4. So if you wanted, you could go ahead and simply now use the derivatives. So dy by dx will be equal to 2 lots now of 1 over the inside function, 3x minus 2, multiplied by the derivative of the inside function, minus 1 over the inside function, multiplied through by the derivative of the inside function. And then it would be a case of tidying algebraic fractions. As you can probably imagine, I'm not going to spend time doing that based on the last effort. But that gives you some idea. You could argue that it's actually as straightforward just to treat this now as a quotient and deal with it, but this is an alternative for you. And often you might be asked to show that it can be written in this particular form. So it's a skill that you might want to look at using. You might be given something slightly more a bit tricky, but in reality it's not an awful lot to deal with. So let's say we had 3 lots of the natural log of e to the power of 5x. If we look at this, this is often something that comes up towards the end of a book exercise just to throw you off. Let's just look now at a bit of logic right here. We could simply write now the inverse equivalent. Alternatively, using the power law, we could say that y is equal to 15x multiplied by the natural log of e. So y is equal to 15x multiplied by 1. So if we want dy by dx, all we're doing is differentiating this linear function, and that will give us 15. So just don't be put off by certain examples. That now is a typical one that you might get thrown. Y is equal to 4 lots of the natural log of, let's say now, 2x, and then we might have multiplied now by e to the 3x. So all you're doing again is splitting this up. Y is equal to 4 lots of the natural log of 2x plus, and we'll just write it here, 4 lots of the natural log of x, plus now the natural log of e to the 3x. You know that the natural log of e to the 3x is just 3x, so y is going to be 4 lots now of the natural log of 2x plus 3x, and we can go ahead and find the derivative. So dy by dx will be now 4 lots of, we're going to have 1 over 2x multiplied by 2, and as we saw, if we got the natural log of kx, the derivative now is just 1 over x plus now the 3. And that's going to leave us now dy by dx will be now 4 lots of 1 over x plus 3, or any equivalent. I'm keeping the constant out as it means that we're not multiplying by 4 all the time, but again, it's entirely up to you. So that now is a typical little quirk towards the end of the book if now they want to get you using particular log and exponential rules. Of course, you might be asked to deal with either products or quotients, and we'll just end up with end the video with just one. Let's say we wanted to find the derivative now of y is equal to, let's go for 3x squared divided by the natural log of 4x minus 1. So here we've got a quotient, and we can use the quotient rule. We've got the form y is equal to u divided by v, where u and v are both functions of x. We can say that dy by dx will be equal to v du dx. So that is the denominator multiplied by the derivative of the numerator, minus u dv dx, which is the numerator multiplied by the derivative of the denominator, all over the denominator squared. So let's go ahead and do this. And again, you don't have to take the 3 in here. You could say that that will be a constant. So what we've got then is dy by dx. So dy by dx, if you choose to take the constant out, will be 3 lots now of, and then we'll put it in here. So we've got u is equal to x squared, du dx, the first derivative, or the derivative of u with respect to x, is 6x. We've got now v, and v is the natural log of 4x minus 1. We can say the derivative dv by dx will be 1 over 4x minus 1 multiplied through by the derivative of the inside function, and we would show full workings. I'm just going to write it out as 4 over 4x minus 1. Now, when you come on to integrating, you will spot now that this is the derivative now of the denominator. So the numerator is some form of a derivative of the denominator, and that will help you with integration. So it's worth bearing in mind later on. So what we're going to have then are these two multiplied. So we've got 6x multiplied by the natural log of 4x minus 1. Then we'll subtract away 4x squared over now 4x minus 1, and we will put all of this now over v squared, and this now is the natural log of 4x minus 1, which we're going to square. Now don't be under the illusion that let's just extend that. that is now the natural log of the value 4x minus 1 squared. It's now completely squaring this whole term here. So that is a derivative, and I'll allow you to tidy that up. As you can see, that's going to be fairly messy, but that's just using now the quotient rule to find the derivative. So there we go, that's just a bit more work now with the exponential and log functions. In later videos we will look at exam style questions when we're finding those stationary points or we're finding tangents and normals. But for now, hopefully that's given you enough skills to move forward. If we just recap, if we have y is equal to e to the x, the derivative is dy by dx. If we have y is equal to e to the function of x, then the derivative is f dash of x multiplied by e to the f of x. If we have now a log function, if y is equal to the natural log of x, then we have dy by dx as 1 over x. If we have the natural log of a function of x, we end up now with f dashed of x over f of x, or the inside function. And that will just give us the derivatives. And you can quote those, or you can use the chain rule.